Hi students, welcome to my lectures on chemical reaction engineering. In the last class, we have discussed about how to deal with the non-elementary reactions. There are two mechanisms, the non-chain mechanisms and chain mechanisms, because in both the mechanisms we have to identify the intermediates and we have to apply pseudo steady state hypothesis to get the rate expression. So, if you please follow my earlier lecture, because this is a continuation of my earlier lecture. And let us find out, as I told you, today is to find out the rate expression. What rate expression? If this is my reaction, azo-methane is reacting to form ethane and nitrogen. Okay. If this is the reaction, my rate expression is my decomposition of azo-methane is equal to formation of nitrogen, which is equal to K3 K1 into concentration of azo-methane square divided by K3 plus K2 into concentration of azo-methane. Okay. If this is the rate expression, how people will come to the conclusions? Because we have to there are 6 steps to follow. Whichever may be the non-elementary reaction, whatever may be the mechanism, if you follow the 6 steps, you can able to find out rate expression for a non-elementary reaction. The step 1. Okay. Assume mechanism, because as you know, the non-elementary reaction will not happen in a single step, it will happen in a number of elementary steps. Okay. First of all, you have to assume what are those different steps, elementary steps. Step 1, assume the mechanism, write down those steps. Second, what is the write down the rate expression. Okay. Because if you are interested in formation of nitrogen, write down that rate expression. If you are interested in decomposition of azo-methane, write that rate expression. That is what is the second rate expression. Third, identify the intermediates. Out of those reactions you have listed, what are the intermediates? List out those intermediates. Sometimes it could be one intermediate, sometimes it could be more than one intermediates. And step 4, once you identify the intermediates, apply the pseudo steady state hypothesis for those intermediates. That means rate of formation of intermediate is equal to 0, as I explained you in the last lecture. Final, once you apply the pseudo steady state hypothesis, you get the final rate expression. Okay. Once you apply the pseudo steady, you get some equations. Finally, substitute those equations in the rate expression in the second step. Okay. Finally, you got the rate expression. Okay. You get some rate expression like this. And sixth step is validity by order. Okay. You have got the rate expression. How do you know that whatever the mechanism you have assumed, whatever the steps you have written down, that is correct or not? So, in the final 6th step, we have to validate with the experiments to found whatever the mechanism assumed that is correct. So, let us do those steps. Step 1, assume the mechanism. Okay. The molecule A is my azo-methane, B is my ethane, C is my nitrogen. A star, that means, is my activated azo-methane molecule. Okay. This is my nomenclature I have given for this azo-methane reaction. Let us, one azo-methane molecule is colliding with another azo-methane molecule and to become one activated azo-methane, one normal azo-methane. And this again, this reaction can be backward also. This is a forward reaction. The backward reaction means one activated azo-methane and one normal azo-methane and colliding to become two normal azo-methane. That means it will come back to the original state. And in the third step, one of the activated azo-methane molecules will be forming to B and C, which is my ethane and nitrogen. These are my assumed steps, right? First step and second step and third step. That means my first step is done. Let us go to the second step. Write down the rate expression. I know second step. That means RB, formation of nitrogen, is nothing but decomposition of azo-methane. In the third step, from the third step, you can see the formation of nitrogen is there. Okay. That is nothing but K3 into Ca star. That is K3 into Ca star. Okay. Now the third step is done. Second step is done. Let us go to the third step and fourth step. Third step is identify the intermediates. Among this, only the A star, the activated azomethane molecule is my intermediate. That means I have identified there is only one intermediate in my mechanism assumed. And fourth step, apply the pseudo steady state hypothesis for the that particular intermediate. That means rate of formation of intermediate, which is di star by dt equal to 0. Here Ca star is my intermediate. So R of A star means activated azomethane molecule is nothing but dCA star by dt. And I told you in the pseudo steady state hypothesis, net rate of formation should be equal to 0. What is the net rate of formation? That is rate of formation minus rate of decomposition is nothing but net rate of formation. So net rate of formation is nothing but rate of formation rate of formation minus rate of decomposition. Okay. What is the rate of formation? In among the steps, in which step the formation of azomethane molecule is happening? Only in the first step. You can see on the right hand side only A star is here. That means only the first step is helping in the formation of azomethane. That is why it is a positive. That is nothing but K1 into Ca square, that is the formation of azomethane, the rate of formation of azomethane. In the second step, minus rate of decomposition. In which step the decomposition is happening? Look into the left hand side, reactant side. In the second step it is decomposing, and the third step it is decomposing. That means reaction number 2 and reaction number 3 help in the decomposition of this activated azomethane. So I have to combine these two. That rate of decomposition is from the second and third step, that is K2 into Ca star into Ca, and the third step is K3 into Ca star. That these should be both. Okay, these are the both reaction that is help in decomposition of the intermediate. So one is positive, these both steps are negative. So now it should be equal to 0. That means if I make this equation equal to 0 and keep Ca star, this is Ca star on the left hand side and every other expression is on the right hand side. Now Ca star is nothing but K1 into Ca square divided by K2 into Ca plus K3. Now simple, step 5, I apply pseudo steady state hypothesis, I found the concentration of the intermediate and final rate expression. That means now you got the Ca star, substitute in the second step, that is K3 into Ca star, that is nothing but K3 K1 Ca square divided by K3 plus K2 into Ca. Now you got the final rate expression. Okay, that is fifth step. Now you have to validate, okay, whether this rate expression is correct or wrong, and let us do that. In the final step, sixth step, that is Rb is nothing but rate of formation of nitrogen, which is equal to decomposition of azomethane. Rb. If you look at the reaction, these are two are the product, this is my reactant. That means rate of formation of nitrogen is equal to rate of formation of ethane, which is nothing but rate of decomposition of azomethane, which is nothing but K1 K3 into C azomethane square K3 plus K2 into concentration of azomethane. Now case 1, how to simply identify my rate expression is correct or not. Let us take the simple cases. In the case 1, that is K2 into azomethane concentration is much less than K3. That means this K3 is much higher than K2 into this one. That means lower concentrations of azomethane. That means low C CH3 twice N2. That means this is the condition where that means K3 is much higher than K2 into C. K3 get cancels out, and finally the rate of decomposition of azomethane is nothing but K1 into concentration of azomethane square. Now you can see these two at low concentrations of azomethane, the rate is second order with respect to azomethane. You can see minus R rate of decomposition of azomethane is K1 into concentration of azomethane square second order. That means if I conduct my reaction, that means rate of reaction with respect to the concentration of azomethane. If I plot rate on y axis and concentration of azo-methane on x axis, it is a curve, second order curve. That means in the experiments also, instead of straight line you get this curve. That means at lower concentration in the reactor, I keep a lower concentration of azo-methane. I will measure what is the rate. If that rate is matching with that of a curve, okay, then that is this equation is valid, okay, at lower concentrations. What happens at higher concentrations? That is, the second case is high concentration of azo-methane, okay. At high concentration, this term is much higher than the first term. In such cases, you can neglect this term. So, what the equation, this equation can become, my decomposition of azo-methane is nothing but K1 K3 into azo-methane square divided by K2 into azo-methane. Now, one azo-methane concentration cancels out. Finally, K1 K3 by K2, it is K1 is constant, K3 is constant, K2 is constant, combinedly it is one constant, which is K. That means at higher concentrations of azo-methane, the rate is linear in nature. That means order 1, that is linear, right. That means if I conduct in a batch reactor at high concentrations of azo-methane, I should get the rate is, that means linear in nature. That means at lower concentrations I have the second order nature, at higher concentrations I have the linear order. That means whatever, if both the cases are valid, and if that is the case, and whatever the mechanism I have assumed, that is correct. If that is not the case, that is, I mean, whatever the mechanism I have assumed incorrect, I have formulate new mechanism, do the similar 6 steps, find out the rate expression and compare with that of a different cases. And let me tell you one more thing. If I combine, don't worry about the case 1 and case 2, whether this equation is correct or not. That means if I plot azo-methane rate on y axis, concentration of azo-methane on x axis, what happens? At low concentration, the rate is, I mean, second order in nature, that is the curve. As the concentration of azo-methane is increasing, the rate is becoming linear. Earlier it is non-linear, and at high concentration it will become linear. So, if you can assume, if you get this kind of curves which is matching with that of a experiments, then whatever the mechanism you have assumed, that is correct. I hope you have learned how to, with simple 6 steps, you can get the rate expression and validation of the rate expression. And thank you. Let us meet at the new lecture.